All right, so I know it seems like forever since we talked about the Big Bang and dark matter and dark energy, let alone the Milky Way galaxy and other galaxies. It seems like forever. So if you're like me and if you have any extra time at all and you want to prepare, bless you, for your test on Wednesday, what I would do actually is go read your textbook, and or I would go listen to some of those videos. Whether it's the documentaries that I showed on pretty much all those subjects, or whether it's me blah, blah, blahing. So, because honestly, this topic, I really wanted to rely pretty heavily on what the documentary said. But let's see what we got for our notes. So dark matter, why do they call it dark? Well, you can't see it. Why do we know it's there? Usually because of its influence on other things, okay? Gravitational influence, most specifically. So dark matter just means it's not glowing in any wavelength, not visible, not infrared, not ultraviolet, nada. Not glowing in anything. So dark energy, and actually, remember what the video said is basically dark energy is why our universe is expanding. The expansion is accelerating. Because remember we said Newton says that you get an acceleration if you apply some sort of force. F is equal to ma. Okay? So actually that force or that energy accelerating our universe actually is dark energy. Again, I mean, what makes it dark? Well, we don't really know the nature of it. We can't sink our teeth into dark energy, but we know it's there because of what it's doing to our universe. So actually energy and matter can be kind of used interchangeably in a sense. If we were to take our universe and to cut it up into what's there with regard to energy and matter, 68% is dark energy, okay? 27% is dark matter. Then actually we have ordinary matter is 5%. Okay, and of that 5%, only 0.5% of, 0.5% of the whole universe is stars. So we have a lot of dark energy and dark matter. Okay, so again, how do we know that dark matter is there? And actually, remember, clear back in unit 1, we talked about kind of our place in the universe, and actually we are a star in orbit in the Milky Way galaxy, and around our galaxy is a bunch of dark matter. So we're actually going to kind of look again at that. The video, I think, did a good job of basically saying we know that there is dark matter surrounding basically all galaxies, each galaxy including ours, because of the way things orbit the center. So what this actually is if you had a rigid body like a merry-go-round, okay, you would go fastest out at the edge of the merry-go-round, and you go slowest with regard to kind of the amount you cover per rotation near the center of the merry-go-round. Although I think it's the center of the merry-go-round that gets you sick. You sit there, if I remember right. Okay, so that's the rotational curve of a rigid body. This is the rotational curve of our solar system. So basically, and this is a gravity thing. This rigid body was not a gravity thing. This is a gravity thing. So one of the things we know that the closer you are to the sun, okay, the faster you orbit. Okay, Mercury orbits the sun fastest. Venus a little slower. Earth a little slower. Mars, okay. Saturn slower. Uranus, okay. Neptune very slow. Okay, and that's all because of the gravity of our sun. So basically, that's a situation where in our solar system, we know that our sun is like 99.5% of all the mass of our solar system. So all the mass is right here. And we get kind of a decay in orbit speed as you go farther from the sun. Okay? So that's actually what they were expecting to see with regard to galaxies. What are galaxies? Well, we got that nuclear bulge, supermassive black hole hiding in the nuclear bulge. Okay? So you would expect, if you're farther from the center of the galaxy, just like Uranus and Neptune, you should go pretty slow. Well, that's not what they found. So this actually is a rotational curve of now stars in the Milky Way galaxy. So notice instead of basically kind of going slower and slower like Uranus and Neptune and Pluto and the Kuiper Belt objects, actually it just kind of has kind of a constant velocity, getting farther from the nuclear bulge, Sagittarius A star, okay? And the fact that it doesn't decay like that means that we basically have matter that is kind of encompassing our whole galaxy. That's what's causing that sort of rotational curve. Okay, so this is a little figure of that little blue thing there is the Milky Way galaxy edge on. You can kind of see the little hump in the blue thing. That's our nuclear bulge. Little red dots out there, actually that's kind of halo stuff. Okay, but the kind of ghosty looking gray thing, that is dark matter. Okay. So this is looking at other galaxies. Do other galaxies have the same issue? And the answer is yes. And you're like, well, how can I understand how stars are orbiting the centers of other galaxies? And the answer is the Doppler effect. Okay, so remember we said that actually here the position A would give us a blue shift. Position C would give us a red shift. Okay, and that's exactly what we see. Blue shift because it's coming towards us, red shift because it's going away. Okay, and from that sort of information, if we're fortunate enough to have a galaxy that it was kind of edge on a little bit, we can get a sense for how stars, how fast they are orbiting the nucleus in their galaxy. Okay, so each one of these colored lines actually is a rotational curve for stars in other galaxies. Okay, and notice they do kind of just flatten out. So again, they're not like the solar system where all the mass is in the center. Okay, they don't have like a decay velocity like that. Okay, so dark matter. We said that galaxies actually are in clusters. Okay. Galaxies organize themselves in clusters, and then actually clusters are organized into superclusters. And so within a cluster of galaxies, we can actually kind of see this dark matter that's strewn amongst the galaxies. One way we can know that the dark matter is there just by looking at the galaxies move. Okay, get a sense for where the dark matter is. Another one is by taking the temperature. So down here, this is actually a cluster of galaxies. Kind of the purple and the blue would be where the dark matter is, okay, by taking the temperature. That's kind of strange to me. The third one, and I think the video did a good job talking about this, is gravitational lensing. Okay, remember dark matter, we don't see it. It doesn't glow in any wavelength of electromagnetic radiation, okay, but we can see its influence, gravitational influence. So gravitational lensing works like this. And again, it just seems like so long ago since we saw the video. But here is your cluster of galaxies, okay? And here are you, us, Earth, okay? Basically, that cluster of galaxies has dark matter strewn in throughout. And it creates kind of a dent in the fabric of space and time, such that this galaxy right here, when that light, okay, goes in all directions, it actually curves around and is bent by the presence of the galaxies and the dark matter, more specifically, that those galaxies are embedded in. So then what happens is, instead of seeing the galaxy, well, I guess we couldn't see that galaxy back there, it's farther away, it's behind those other galaxies. We actually do see an image of the galaxy right there because of its light being bent. And we see actually kind of a pair of images shown here. Okay, that is called gravitational lensing. Kind of like our lenses actually bend light to a certain, just the right point in our eyeballs. Okay, that's what dark matter is doing, strewn in those galaxies. So this is showing you gravitational lensing. Those little blue wisps actually are galaxy behind that galaxy cluster. I think that is so cool. And you know, one of the things about looking farther away from us, actually, we are seeing the older and older, or younger and younger, we are seeing galaxies as they were shortly after the Big Bang, the farther away we look at them. Gravitational lensing. So, dark matter, legit or not? Well, if it depends upon gravity, okay, then if it's not legitimate, then we got gravity totally, we don't understand gravity. But since we do understand gravity, it must be legitimate, basically. Our understanding of gravity is pretty solid. It is, but it isn't. I watched a documentary, should stop watching those, the other day about subatomic particles. And okay. So what is it? Dark matter. And actually, hopefully, this will ring some bells with the video we saw. What is dark matter? It doesn't glow. Well, it could just be normal stuff that's not glowing. Okay, normal stuff is called baryonic matter. And I know that's a Star Trek term. I just know it is. Okay. Normal atoms and electrons, protons, neutrons. Okay. But they don't glow, so actually some of those could be what we call massive compact halo objects, otherwise known as machos. So of course halo means the region outside the disk of a galaxy. That's the halo region. Massive because they're creating gravitational influence that we're seeing, we're calling it dark matter. Compact meaning they're just very dense, okay? So some of that stuff probably is machos, but there is not enough machos to account for, not enough baryonic matter to account for all of the effects of dark matter that we see. So probably then the rest of it, most of dark matter is actually what we call WIMPs, weakly interactive massive particles. So remember the video we saw where the guy down in like a coal mine basically was trying to capture the influence of some of these WIMPs? I just think that is a cool term. You know, so dark matter is all around us, passing through us, weakly interacting massive particles. Okay, so like I said, machos or WIMPs, isn't that cool how it's machos or WIMPs? It's like, is that not funny or what? Yes. Probably both, but definitely that sort of odd sort of particle that still trying to get a fix on. Now, I actually, just a week ago or so, looked this up. Do you remember the Higgs boson particle, the God particle, back like 2 years ago? The Hadron Particle Collider, actually the folks, physicists were really excited too. They had found a new subatomic particle called the Higgs boson. And they were hoping that that would actually be one of the missing pieces to kind of resolve some of this issue with WIMPs. And I've read a couple different things I posted on the Twitter feed that not necessarily, I guess is my point. So I like this topic, remember, and I'll put this whole thing up here. Okay. Remember the video kind of talked about how dark matter was probably important for galaxies to form? It was like the scaffolding that galaxies formed around. Now remember what galaxies are. Our galaxies are just an island of stars, okay? So basically kind of dark matter is responsible for ultimately the stars within the galaxies forming. So this right here, this is so cool. These little yellow dots here are all galaxies. So this is kind of how galaxies are distributed, okay, in our vicinity. So what we see is that galaxies kind of, like scaffolding, are kind of like organized. So galaxies, of course, are clustered into galaxy clusters. And then galaxy clusters are clustered into superclusters that all kind of go on what we call filaments around large void areas. So like if you were in a Star Trek episode and somebody said, oh my gosh, we're entering the void, okay? There are actually kind of regions in outer space, okay, where there are no galaxies, okay? Void regions. I just think that's so cool. So this kind of goes back to the Big Bang and the expanding universe. Remember that our universe used to be very small and very hot. Okay, this is 0.5 billion years after the Big Bang. Okay, so notice after the Big Bang it's expanding. Now these are not all on the same scale because notice this is 13 million light years and this is 140 million light years. Okay. So kind of what you're seeing is the space and time of our universe is getting larger, and you see over time it got cooler, and it had to cool, remember, in order for atoms to form, let alone molecules, let alone stars, let alone galaxies, okay? That's kind of what you see here. This last one over here then is kind of the, this one you can almost kind of see some void areas and kind of filaments of how the galaxies are organized. All right, so last one. Actually, there are 4 models on kind of all associated with the Big Bang and associated with our expanding universe. So this, I think, probably is when I was coming through this course years ago at the University of Northern Iowa, they probably talked more about a recollapsing universe. I think the video might have even talked about that. Basically, what a recollapsing universe looks like is down here, this is your Big Bang, okay? And right here is where we are, okay? Oops, right there, that's where we are. It's going to continue to get larger, okay, and then it's going to come back together again. And I remember it was a lady scientist who basically said, and so maybe it's done this many times. It's going to come back together and come back, you know, okay. So, but honestly, we've been saying that our universe, there's significant evidence that said it's about 13.7 billion years old. Okay, about 13.7, 13.8 billion years old. This sort of model actually sets the Big Bang at not that far ago. This is actually the youngest model. It's called the Big Crunch. Then there's this one. And whether it's going to come back together again, recollapse, or whether it's going to coast forever, okay, kind of depends upon how much mass and matter there was at the time of the Big Bang. So the critical universe basically, notice that it doesn't come back together again. According to the little figure, you can see it just basically kind of stays, it will eventually stop expanding and stay the same size. Okay? The coasting universe, notice the difference between the critical and the coasting, is that the coasting, it keeps getting larger and larger and larger. Okay? And again, this all has to do with how much matter there was or was created early on in our universe. So notice these actually were getting the Big Bang longer and longer ago. So this would be an older Big Bang, okay, and the first one is the youngest. The 4th model, though, honestly, is what makes most sense based upon what we know now, not what we knew, 20, 40 years ago. Okay? So notice that it's getting larger, but notice that the getting larger is what we call accelerating. Okay, that's kind of the isentropic kind of curve that we see. Okay? So it's getting larger at a faster and faster rate. Okay, and that actually, in this scenario, that gives us our 13.7 billion years old. Okay, so there is more than just one reason to think this accelerating universe is, of the 4 models, is the most correct. One of the reasons is actually goes back to using those, these are, I'll put SN for supernovas, I'll put white dwarf supernovas. Actually, our white dwarf supernova data most closely aligns with this yellow one. So I guess then, and this did make it to your test, what is causing this acceleration? Why is our expansion not just staying the same, but actually accelerating? And the answer is dark energy. I think it's a multiple choice question. Okay, was that the last one? Yeah. Okay. So we got time to go ahead and knock out